Look at this shipping port. In a consumer packaged goods supply chain, every one of these containers generates a cascade of data. Reconciling that data at high volume creates a massive computational bottleneck. To pay a carrier, a company has to execute a three-way match. They must verify that what they ordered matches what shipped, and that what shipped matches the final invoice. Executing this automatically means crossing entirely separate multimodal systems. As we see in this diagram, the pipeline chokes because the data lives in three distinct realities. We have highly structured purchase orders in the ERP, proprietary routing and rate logs in the internal transportation management system, and completely unstructured carrier invoices arriving via email. Attempting to force all this information into a traditional monolithic cloud warehouse to run these matches introduces severe network latency, the compute cost spike, and the pipeline stalls. We can solve this integration problem by building a highly specialized analytical architecture using the DuckDB stack, augmented with semantic machine learning layers. We are going to build out this system blueprint step by step. We will track a single freight invoice from its chaotic ingestion all the way to a fully audited cloud-scale data product. Removing this data friction turns supply chain accounting from a retroactive cost center into a real-time operational advantage. Take a look at this standard carrier freight bill. The pipeline begins here, in absolute chaos. Documents arrive as scanned images, heavy with unstructured layouts, varied fonts, and deeply ambiguous line item charges. A carrier might bill you for a peak diesel adjustment. Your internal system, however, only recognizes a fuel surcharge. It is the exact same fee, described in completely different terms. If you try to write deterministic logic or regular expressions to catch these discrepancies, the system will break. Carrier naming conventions evolve too rapidly for hard-coded rules to keep up. Here is the first step of our architecture. A multimodal vision AI extracts the raw text from that chaotic PDF and formats it into a highly structured JSON payload. But structure alone isn't enough. We need meaning. The JSON payload is then passed to a vector database, like pgvector. The database converts the extracted text into vector embeddings. It maps the text into a vector space, allowing a phrase like peak diesel adjustment to snap directly to its nearest semantic neighbor, your internal general ledger code for fuel surcharge. We have to bridge this semantic gap first. Without this AI layer, the downstream engine ingests corrupted inputs, and every high-speed join it attempts will fail. Now that our data is perfectly clean and standardized, we can process it against the company's internal records. This schematic introduces our central compute node, DuckDB. It operates as an in-process vectorized columnar OLAP database. DuckDB ingests the ERP purchase orders, the TMS routing data, and our normalized invoices. It executes three-way quantity matching, verifies contractual rate lanes, and audits accessorial fees, all in a matter of milliseconds. Because it runs completely in memory on standard compute, it entirely bypasses the network latency and steep querying costs associated with routing this workload through traditional cloud data warehouses. However, this performance relies on a strict architectural constraint. DuckDB is designed specifically for a single-node in-memory environment. If you attempt to run multi-terabyte unindexed cross-joins across these massive logistics datasets without properly managing storage spillovers, you will instantly saturate the available memory and crash the microservice. DuckDB gives us the exact analytical speed we need to reconcile millions of records, but because it is a stateless engine, it cannot manage real-time human workflows. This brings us to a rigid rule in data architecture. Analytical processing, or OLAP, must be strictly isolated from transactional state management, or OLTP. Analytical engines are built to read massive columns of data simultaneously. If you force an OLAP engine to pause and manage continuous row-level updates from a human clicking approve or deny, you destroy its join performance. Looking at the next phase of our diagram, we solve this by introducing PostgreSQL. It serves as our distinct operational state store. PostgreSQL handles the workflow outputs. Down the screen path, it tags the perfectly matched invoices and passes them straight to the payment execution system. Down the red path, it maintains the human-in-the-loop exception queues. If there is a dispute or an escalated charge, PostgreSQL tracks the live workflow status as users review the discrepancies. Because this branching happens asynchronously, DuckDB can continue executing its matching roles at full volume without ever locking the operational tables your staff is actively using. By keeping the transactional database entirely separate from the analytical database, human workflows can never throttle the machine speed reconciliation engine. Moving past the real-time processing, we have to address post-processing financial compliance. Every freight platform requires strict, undeniable audit trails. When auditors review these transactions, they require proof of exactly why an invoice was approved. You have to be able to pull the precise contract rate card that was active on the exact date of the shipment. This diagram layer shows our solution, Duck Lake. This acts as our dedicated storage and auditability layer. Physically, Duck Lake stores columnar parquet data directly on object storage, while maintaining a lightweight relational metadata catalog to track the file locations. The critical compliance feature here is snapshot isolation. Every time a new verified result is written to this layer, the system generates a permanent, immutable snapshot of the data. This means you can isolate a single file node and pull the exact mathematical state of a contract rate exactly as it existed on June 1st. Auditors can execute point-in-time, time travel queries directly against these historical states, pulling perfectly preserved records. Achieving this level of auditability through metadata catalogs is vastly superior to the traditional method of maintaining heavy, highly complex duplicate temporal tables. It effectively transforms passive object storage into a fully compliant, queryable financial ledger without burdening your systems with massive compute overhead. This diagram reveals our end-to-end blueprint. Vision AI and vector databases turn unstructured documents into structured data. DuckDB executes in-memory analytical joins, while Postgres manages workflow states. Duck Lake guarantees immutable historical auditability, and MotherDuck extends this architecture into the cloud. MotherDuck functions as a bridge. It allows local worker nodes to query the central Duck Lake storage layer, enabling the distribution of broad, interactive data products. This setup allows business users to access high-level cloud analytics, pulling live dashboards on carrier compliance, supply chain spend leakage, and route rate optimization. Many engineers assume that a pipeline like this requires relying entirely on a monolithic cloud data warehouse. But offloading high-speed, line-atom logistics matching to those external systems only introduces network latency and unnecessary compute costs. Modern enterprise AI relies on specialization. Building a truly performant system means moving away from the monolith and marrying OLAP, OLTP, and vector operations into a tightly coupled, highly specialized architecture.